All right. So today we have a kind of mixed program. So I thought I first wanted to finish off what I very briefly mentioned last time, just the power counting issue to settle this. And then I want to talk a little bit about integration by parts, although I do understand that Claude has spoken about this in the last school, and I think, well, if you have any question at that stage, then please ask me when I'm at that part, but I will keep it rather short. And then hopefully we have time in the end to start looking at some actual Feynman integrals and the analytic aspects of iterate integrals and how you can use them. But most of that will be coming tomorrow in the lecture, but I want to get it started today. So let me just remind you of what I said yesterday about the power counting issue. So we looked at this example of a triangle graph. That was motivated from the calculation on Monday where we looked at the g minus 2 calculation. So suppose we have these three external momenta, p, p prime, and q. And we have three edges here. Let me call this edge 1, this is edge 2, this is edge 3. And this is I want to think of this as my overall graph. And then we want to look at the power counting and what happens when we send some Schwinger parameters to 0, or equivalently when we send some momenta to be large or small, depending on the situation. So let me look at this graph, and let me look at the subgraph. So by little gamma, I just denote a subgraph. And I want to look at the subgraph which consists of the edges 1 and 2. So I take the edges 1 and 2. So as a graph, this looks like this. So it's just missing the edge 3. And the question was about the power counting. So remember, what is the f polynomial of g? Well, it had this term which is u times some linear form of the masses. So there is a ug. Remember, ug is just x1 plus x2 plus x3. And then we have m1 squared x1, m2 squared x2, m3 squared x3. And then you have terms p squared. So this is this 2 forest thing, right? So how can we cut this graph apart? So for example, we can delete these two edges, 1 and 3, and then we separate into two trees, and we have the momentum p running from this part into this part. So this cut gives me this contribution p squared x1, x3. And similarly, we get a p prime squared x2, x3. And then there is a q squared x1, x2. And now we're looking at the situation where we send x1 to row x1, x2 to row x2. And we want to send row to 0. So you want to see what happens with this graph polynomial with the second semantic f when these variables become small. So what happens? Well, I mean, every x1 gets a factor of rho. x3 does not get a factor of rho. So somehow x3 is a term that remains. Everything which is x1 or x2 vanishes in comparison to x3. So in this limit, we only have to keep x3 here. And also from here, right, x1 and x2 vanish in comparison to x3. So we only get x3 squared m3 squared. And from here, actually all of these terms vanish in the limit, right? Because every one of them gets a row, or this one even gets a row squared. So the leading order in this limit, the f polynomial becomes a very simple expression. And what is this? We can interpret this because we can write this as x3 times x3m squared. And this here is, it looks stupid, but this is the u polynomial of the graph which has just the edge 3 as a tadpole. And this is x3 times m squared. So this whole thing is actually the f polynomial, which only consists of the mass term in this case of this tadpole graph. So this is this factorization that I said, that this leading order in this limit of the f polynomial is actually a product of the f polynomial of the quotient graph. So this graph here is the quotient graph g by gamma, right? So if you squish all of these vertices into one big vertex, which is this node here, then suddenly the edge 3 becomes an edge between the same vertex with the same endpoint. You get this tadpole thing. And then because you have all the external legs are now attached to this one, but all the momenta sum to 0, right? So there is actually no momentum on this one anymore. So the only kinematics you have here is the mass of this edge, and this is why this is the F polynomial. So this is the generic situation. So you have a vanishing. There's actually no vanishing. F doesn't vanish. There's rho to the 0, right? Because the subgraph is 0 loops. This was this counting that I mentioned. Now we have a special situation. Now let us set M3 to be 0. But of course, if we set M3 to 0, as we did, then of course this term vanishes. Sorry, this is M3 squared, right? And then of course, even though we have this factorization to the order of rho 0, it's useless because actually the coefficient is 0. So we have to look at the next order in rho. So let's do this. So what happens if we set M3 0 and we don't have this? So now we have to pick up all the linear terms in rho. So how do we get linear terms in rho? Well, this term has gone anyway. So we have linear terms in rho here. So if we take also rows from here, we get rho squared. So we only keep the x3 from the u and what's there. So we have the x3 m1 squared x1 m2 squared x2. And then here this becomes a rho squared. So the linear terms in rho are only these two. Okay. So now indeed we have a vanishing of rho with to the power 1, which is this final formula I gave last time. And the claim is that again there is a factorization, and indeed you see this because you can rewrite this as rho times x3. You can factor out this x3 here. And then you're left with m1 squared x1, m2 squared x2 minus p squared x1 prime squared x2. And now again, this thing here is the u polynomial of this tadpole graph. And this here, is when you think about it, is the f polynomial of the subgraph. So this is the f polynomial of gamma, of little gamma. Yeah, it might look weird, but if you don't have any loops, then the f polynomial is very simple to write down. Because there's only one spanning tree, which is the entire thing. There's nothing left out. So u is 1 in this case. So the mass term is just the sum of the masses squared times the variable. So this is the mass term. And then, I mean, there's only two fours. So you either cut this edge or you cut this edge, and you get these two terms. So indeed, you also see, again, we have this factorization. Now it's a different factorization. Here, we got the f polynomial of the quotient graph. Here we get the f polynomial of the subgraph times the u polynomial of the quotient graph. And we get an order in rho higher. And you can classify when this happens. So how can it happen that f of the quotient graph is 0? Right, so this is the situation here. Yes, right. So the quotient graph itself doesn't have an f. The f vanishes. Well, in order for this to vanish, we must have all massive edges must be in little gamma. Because if there would be any massive edge left, it would remain in the quotient, and it would give a non-zero contribution to the f polynomial. Right? Because if we have such an edge, we would have me squared xe u contributing to f. So f couldn't be 0. Also, there can be no momenta, external momenta running through the quotient. Right, so here this happened because all the external legs were contracted to one vertex, so the momenta sum to 0, so there is actually no momentum dependence anymore of this graph. as long as we do have a momentum, we get a non-zero contribution to the F polynomial, right? And now, if you don't have, unless you have a special configuration, this can only happen if the subgraph connects all the external legs, right? So gamma connects all external legs. Right? So if gamma would not connect all external legs, so if you have your graph G, there is some external leg here, and there is another external leg which is not connected by the subgraph. That means that if you contract the subgraph, they are still not connected, so there is a cut in the quotient between these two legs, and then this cut will contribute some momentum flow to the F polynomial. Now these graphs, so little gammas which fulfill these two constraints, you might call them, so Francis Brown calls them mass momentum spanning. Because they contain all massive legs, all massive internal propagators, and they connect, they span all external legs. But I think in the older literature, these are usually called infrared divergent subgraphs, or infrared subgraphs. So there is a reason why somehow whenever you have the situation that the quotient has no kinematic dependence, that it's somehow, the intuition is more like towards that this should be considered as an infrared divergence, like a soft divergence. Whereas as long as this is non-zero, in a physical interpretation, it more corresponds to UV divergence. So you call a graph which is mass momentum spanning, also you call it an IR graph, and the other ones are UV graphs. And they change the power counting. And then if you have such a graph, because of the changed power counting, the condition changes. So for an IR graph, for an IR subgraph little gamma, the convergence condition, so the power counting that you need in this corner of integration space, so it gets modified. So we call it the infrared degree of convergence. And this is the usual UV degree of divergence minus the overall degree of convergence of the total graph. And you can convince yourself that this is the same as minus the degree of convergence of the quotient graph. So in our example, the subgraph is just a tree graph, right? It has two edges, 1 and 2. So it's the degree of convergence is just the sum of the edge powers minus half dimension times loop number, but there is no loop in the subgraph. Now the omega of the total graph is n1 plus n2 plus n3 minus d over 2, because this does have a loop. And so the difference, if you work it out, is exactly d over 2 minus n3, which is exactly minus the superficial degree of convergence of this tadpole graph, which is the quotient. And the power counting condition is that this should be greater than 0. Right? And as I said last time, you can use these power counting conditions to avoid all of this looking at the Newton polytope. So the theorem is that if the external momenta are non-exceptional, so by this I mean they're not 0, they're not on any mass shell, so they're generic. Yeah? Then the Feynman integral converges precisely if for all subgraphs you have the condition we have to write it down in two cases. So either we say we want that this infrared degree is greater than or 0, is greater than 0 for the cases where gamma is an infrared subgraph or mass momentum spanning. And in the other cases, we just ask that the usual degree of convergence is greater than 0. And so this is a totally combinatorial condition which you can work out, which characterizes the convergence. Obviously, there is a lot of subgraphs in a graph, and many of these conditions will be redundant, so you can actually restrict yourself to a very small set of subgraphs which you only have to check, which is enough. So you can actually really identify the facets of the Newton polytope in this case with a particular class of subgraphs that are even further special, but I don't want to go into the details of this. So this was all worked out by Speer in the 60s. Now, so this is the nice situation where everything is easy. So you have these nice characterizations of the divergence degrees. You have the factorizations of the graph polynomials. And this is a situation where you can also talk about motivic amplitude. So I think Claude probably mentioned this last time. And I'll see how much I can mention about this tomorrow. But there's a whole idea of thinking about Feynman integrals in a motivic or algebraic geometric sense. And this is so far only understood in this world. So if you're in this universe where you have these factorization properties of the polynomials, then you can really study these Feynman integrals in an algebraic framework. You can write down a wonderful model, a desingularization of the graph hypersurface in this case. So if you have any questions about this, I encourage you to ask me in between, because I probably won't have much time to talk about it tomorrow. But I'm just trying to convey the message that this factorization that you see there, it's very important for several reasons. So it's important to give a geometric and motivic meaning. So if you want to talk about the symbol or the motive of a Feynman integral, currently we only know how to do that properly in these cases. And secondly, these factorizations obviously have a physical meaning, because they tell you that residues of Feynman integrals actually factorize into other Feynman integrals. So that's also important. So let me just mention one counterexample, which is exactly what I wrote down at the end of the last lecture. Yes? Oh, thank you. This is tomorrow's lecture plan. It will get longer overnight, don't worry. So the counterexample from last time was, well, we still had the triangle, but we had on-shell external x, right? So we had p squared equal p prime squared equal m1 squared equal m2 squared. Yeah? And of course, what happens, you see immediately that now the f of the subgraph becomes 0, right? So even though we have this formula is still true, right? So the graph polynomial, this limit becomes x3 times something plus something of order rho squared. But it's not the leading term anymore, because the leading term vanished. And now if you work out what this rho squared term is, this is what we had last time, which is why we have an extra power. Yeah, so you should note that so specializing kinematics yeah, so for example, sending a mass to 0, or sending a momentum to 0, or sending a momentum on shell. Yeah, specializing the kinematics changes the power counting. That's simply because some monomials in the F polynomial suddenly disappear because they have coefficient 0. So the Newton polytope changes and everything changes. So you will have different singularities. Yeah, so in particular, limits of kinematics, or limits in kinematics, and limits in the analytic regulators, like dimension or these indices, they do not commute. So if you do a calculation in dimensional regularization and you calculate, for example, the triangle integral with everything off shell, you thought you might have been done with the triangle integral because you computed in the most complicated case. But in a sense you are, in another sense you're not, because if you want to compute it in a singular situation where you have massless legs and massless or maybe onshore external momenta, then the integral is actually divergent, and it only makes sense after analytic regularization, and then you have some poles in epsilon. And you cannot directly drain out those poles from the expression you had for the off-shell object. I mean, there is a relation between the two, and you can try to connect the two things, but it's a very different game you're playing. So suddenly, as soon as you hit a 0 here or an on-shell, depending on the graph, you might create new poles in epsilon, so you completely change the structure of the meromorphic continuation. So I hope this is clear why this happens. So not only do we have this problem that we have another power counting, but also in these more general cases, the factorization gets lost. So in this case, there's a miracle that you can still interpret this in some way, but in general it doesn't. So for example, look at an example that I'm sure every one of you has seen at some point. Let's look at a one-loop box integral. So you have P1 and P2 coming in, P3 and P4 coming out. And we considered in the case where all the masses, internal masses, are 0, and we also put the external legs on shell. So now we're only left with the dependence on two Mandelstam invariants. So let me write this down. Let me call these internal edges 1, 2, 3, and 4. What is the F polynomial then? Well, there's no masses. Even the individual external legs are on shell. So the only thing we can do is cut across two legs. So we can, for example, delete the edges 1 and 3. So then we have momentum P1 plus P2 flowing through this cut. So we have minus P1 plus P2 squared. And the edges that we have cut are x1 and x3. Or we do the other thing. You can also cut across here. And then we have momentum P3 minus P1, x2, x4. This is the entire F polynomial with our Mandelstams. So it's S, x1, x3, T, x2, x4. And now let's look at a case. So this is our big graph. Let's look at the subgraph, which is just a corner, which consists, say, of the edges 1 and 4. These are these two graphs. All right, so then the quotient graph. So we contract this part of the graph into one big vertex. So only the edges 2 and 3 are left, and they go to the other vertex where P4 comes out. So the quotient graph looks like this. So this is the original vertex with P4. And now this is a big fat vertex, which was the entire corner. And we have edges 4 and 2 left. And now we have 3 momenta attached to this vertex, but of course by momentum conservation it's the same as if P4 comes in. So now we have a case where the quotient graph actually does have 2 external legs. So it's not mass momentum spanning, right? So this graph is not mass momentum spanning because it does not connect the fourth leg. So in a general kinematic situation, this would have a non-vanishing F polynomial because there is a momentum running through. But in our case, this momentum is light-like. So there is actually no kinematics in this case, right? So the F polynomial of this massless bubble with a light-like momentum is 0. So this is a case where even though the graph is not mass momentum spanning, we have a vanishing here. And you also see that there's no factorization. Because what happens when our subgraph 1 and 4 get small? When 1 and 4 get small, right? So this is just because there's exactly 1, 1 here and 1, 4 here. So both terms scale the same. So we just get out a row minus S x1, x3 minus T x2, x4. So there's actually no factorization. You don't get a separation of the variables from the subgraph from the quotient graph. Whereas in all the other cases, when you do have these factorization formulas, you just separate the problem into the subgraph variables and the quotient graph variables. So this doesn't happen here anymore. So this is just to illustrate why there is a difference in the treatment of these cases. And of course, you can still define these box integrals as motivic periods, but the problem is there's several choices you can do, and it's not there's not a unique way to do it. And then the question is whether you can come up with a definition that is compatible with everything you want on the nose. So I don't want to dwell more on this. I just wanted to illustrate some of the differences in these cases and how the power counting and factorization works. Are there any questions on that kind of story? Then we do something slightly different. Very good. So in the next, hopefully not more than half an hour, I want to say a few words about, oh yeah, no, let me give you an exercise. One exercise. Exercise. Find the divergence in 4 dimensions of the following graph. This is called the Mercedes graph. Can you see this? So it's a propagator graph. It only has 2 external legs and 1, 2, 3, 4, 5, 6, 7, 8 propagators. So it's this graph, and all masses are 0. Yeah, so it's one of the simplest Feynman integrals that occurred in the very early work on the very first paper, Integration by Parts. If you look this up, this graph shows up. So this is in the Mincer program that's used to compute beta functions in the olden days. And the claim is that this simple thing, there's nothing on shell or whatever, but it has a soft infrared divergence. I just try to do the power counting and find the constraint here which is violated, which shows you that this is divergent. Okay. Yes.
So this factorization structure, say like having understanding whether the integral is convergent, has some implication on the actual integrated result, the final result.
Could you say the question again? Sorry, I was.
This structure defined was for understanding where the integral converges, right?
Yes.
So has like and we sort of develop factorization.
Yes.
Does this kind of property have some other implication besides the knowing better where the integral converges? And also like tell us something about the result, the integrated result.
Yeah, I mean the factorization becomes a literal factorization of the integral, of the integrated function. Maybe I should say this more clearly. So I think I mentioned last time just in passing maybe that the fact that these polynomials factorize means that the higher order poles in epsilon, or your regulators, factorize into products of things which come from sub and quotient graphs. So in a way you could say, I mean the very same formula appear in this whole Grassmannian story with factorizing residues of canonical forms. It's always the same kind of phenomenon. I don't want to write down the formula on the board because it's wrong, because you have to forget kinematics on one side, but I'll do it anyway.
In this case, the boundary of a region of convergence.
Yes.
Like
Yes, you have your space. So you can think of the Feynman. So think of the Feynman integral as a function of dimension and these indices. And now think of the space where these indices in the dimension live. Then in the space you have this polytope, this Newton polytope that we talked about last time. And inside, the function is nicely holomorphic, well-defined, the integral converges. And as soon as you go to one of the facets, so when you approach one of these hyperplanes, you hit a pole. And the statement is that all of these poles are simple poles. I mean, you might be confused because you know of higher order poles in epsilon, so something like 1 over epsilon squared or 1 over epsilon cubed. But this is only because you substituted integers for the n's. If you treat all of the n's symbolic, there's only simple poles. Feynman integral is only simple poles if everything is symbolic. So this is specialized, they can coalesce and make fake higher order poles. But originally every pole is simple, and then you can talk about the residue at the simple pole. And then you just get the integral associated to this facet, to the polynomial that you get from only keeping the monomials on this facet. But because it factorizes, it actually factorizes into two Feynman integrals. So you can say, so let's look at the Feynman integral. So it depends on n and d. And now suppose we know that if you have a subgraph and say it's a UV subgraph, then we know that if we move around the n's and the dimensions such that the subgraph becomes singular, then we have a pole. So we can look at the residue of this function at this hyperplane. And the point is that the residue there of the graph actually factorizes into the integral of the subgraph. And then, of course, it only depends on the ends of the edges in the subgraph. But let me just write it like this anyway. And times the Feynman integral of the quotient graph. I mean, the caveat here is that you have, in the UV case, actually, the subgraph does not depend on kinematics anymore. So you make the subgraph a vacuum graph. So you forget about the external legs or masses here. If you have an infrared graph, it's the other way around. You put all the kinematics in this vector and not in that. Yeah, but if you think about the poles in epsilon, it means that if you have a pole in epsilon that comes from here, it tells exactly that the coefficient of the 1 over epsilon pole is the leading order terms in the epsilon expansion of these things. Yeah, so it's a geometric reason why higher order poles come from lower loop or simpler graphs. Yeah. Which, of course, in renormalizable theories is in itself a very important story. But this is the geometric incarnation of it. OK, so let me just lose a few words on integration by parts. So please, everybody raise their hand if they know integration by parts in momentum space, or if they have seen it once, at least. Yes, very good. So let me not talk about that. Or let me comment on it briefly in a second. Let me just do something slightly less usual, maybe. So let's look again at the one-loop bubble, which I know you can write in terms of gamma functions, but bear with me. And we had our Lie-Pomeranski representation for this thing. So there was some gamma factors. Which we had here. And then let me just slightly rewrite this thing. So maybe use an ugly notation. Might be nicer ways of doing this. So remember, what was the formula? The formula was these gamma factors times the integral over the usual integration measure we have in these parametric formulas. So I define this M, which stands for Mellon transform, of some function f. I define this to be the integral 0 to infinity x1 n1 minus 1 dx1 over gamma n1 0 infinity x2 n2 minus 1 dx2 gamma n2 times f. Okay? So the idea is f is a function of the x's. And if you have a function, you can compute its Mellon transform. I mean, the textbook definition of the Mellon transform doesn't have these gammas in the denominator, but of course that's just a factor. It doesn't affect the integration. Yeah, so you can think of this as literally just the Mellon transform. So in the Lie-Pomeranski representation, the Feynman integral is up to some gamma factors. It's nothing but the Mellon transform of a polynomial. And this g, remember, this was just a polynomial given by u plus f. Okay. And what is it in our case? Well, in this particular case, it is x1 plus x2 minus p squared x1, x2. And now let's do integration by parts in this representation. Okay, it's a two-dimensional integral. We all know integration by parts. This should be easy. So what are examples of integration by parts? Well, for example, let's look at this thing. So integration by parts in Schwinger parameters. What can we do? Well, for example, look just at the x1 integral. So forget about x2 for the moment. And suppose we have a derivative acting on f. Suppose you have this situation. Then we can do an integration by parts and rewrite this. Right, so we integrate, so we just forget about the derivative. So you have minus x1 n1 minus 1 over gamma n1 f from 0 to infinity. And then we take the derivative of this thing. We have the integral. Now the derivative brings down an n1 minus 1. And we have f. And now remember there's a functional equation for gamma. So gamma is actually the same as gamma of n1 minus 1 times n1 minus 1. So we can cancel the n1 here by shifting the denominator with minus 1. And then we realize that this is the same integration kernel we would have gotten if we just decreased n1 by 1. We decrease it in the exponent and the gamma factor. Okay. So this term on the right-hand side, this here, well, this is like the, okay. So we recognize this as a shifted thing where we just reduce n1. What about the boundary term? Well, in general, of course, it's hard to say. In general, it might be divergent, it might be convergent. But of course, we assume that we do this in a region where the integral converges, otherwise we cannot do integration by parts anyway. So we assume that this converges. Then you can work out, just because by the fact that this converges and how it behaves at infinity, that actually this thing also, that f must fall off sufficiently fast at infinity to make this integral convergent. And then you can conclude that also the boundary limit here at infinity must converge. Now what happens when it goes to 0? Well, I mean, as long as n1 is bigger than 1, of course x1 at 0 will vanish this term, make this term vanish, unless f maybe has an explicit x1, which might cause problems. But the point is that there exists some region in the n space where this boundary term is 0. So this is the whole magic. So we conclude that if we do this Mellin transform of a function f, of the derivative d by dx1 of a function f, then we get the same thing as the Mellin transform where we've just decreased n1 and we had Mellin transformed f. Yeah, so the right-hand side is the second term. This is just what I've written on the left. You know, I mean, x2 didn't participate in this integration by parts, right? So it doesn't matter. And the point is this is an identity that holds everywhere, right? So you have to be careful that both expressions, both on the left side and on the right-hand side, these are integrals which are in general divergent. But we have discussed in the last lectures that there exists a non-empty region of n's where they do converge. So you're saying that we have two functions which may be defined on different domains. They both have meromorphic continuations, and they both coincide somewhere. That means that by uniqueness of analytic continuation, they have to be equal everywhere. Yeah, so this is a very simple argument, but it's very important. It means that you never have to worry about whether some boundary terms are actually 0 or not, because you can just assume you move to a point where they do disappear, and only there does the integration by parts make sense anyway. And then you can keep this identity and use it everywhere. Yeah, so I hope I've convinced you that this is a proof. So there's no fishiness about this kind of argument here. Now we did integration by parts here, okay. And there is another very simple thing you can check. If you take the Mellin transform of a function multiplied with a parameter, well, instead of thinking of x1 times f, you could also think of putting this x1 of your integrand and treat it in this term of the measure. So you just increase n1 by 1. Of course, it's not exactly the same because if you increase n1, you also get a factor from the denominator, so you have to cancel that. So what you find is this is the same as n1 times the Mellon transform, n1 plus 1, n2, f. And if you combine the two, you find that the Mellon transform of this particular combination, when you take x1 d by dx1 of f, so this is a concatenation of the two things we discussed earlier, and this is the same as just multiplying with n1. Okay. So this is very simple algebra, but what it tells you is that if you act with any differential operator on the integrand of a Mellon transform, you can translate this by integration by parts into a difference equation. So into an equation of the Mellon transform thing and shifts of its argument by plus or minus integers. So this is exactly what the Mellon transform does. It translates differential equations to difference equations. So which means that any differential equation you can write down for the integrand gives you a difference equation for the Feynman integral. So one advantage of viewing it in this form is that you have an immediate proof with this analytic continuation statement that doesn't require you to worry your head about what does it mean to use Stokes' theorem into non-integer d-dimensional space and things like that. So this may be my purely personal taste, I realize that, but since you all have seen the other approach, I just wanted to show you this alternative. Is it already? Yeah. Do I already want to take? Let me do one thing for 5 more minutes and then we take a break. So one thing you should notice about this kind of formalism is that the way I've written it down, again, it has nothing to do with Feynman integrals. And indeed, in mathematics, this has been studied in different forms. So if you ever come across a hypergeometric function, you know there's things like contiguous relations, which tell you that the hypergeometric function has some shifted arguments. I mean, in the analytic regulator kind of arguments, not in the Z argument. So if you shift these regulator arguments, then you can rewrite them in terms of just, in the case of 2f1, just of two basic 2f1s. Everything else can be related to those. So integration by parts are like contiguous relations for a very special set of hypergeometric functions which you get from integrating these polynomials from Feynman graphs. Now let me just do one example. So in this example of the box, of the one-loop bubble graph, let me define the following operator. That's a differential operator. So it's minus p squared 1 minus x1 d by dx1 minus d over 2 x1. That's a differential operator. And I give it a couple more terms. 1 x2 d2. Sorry. So this is a little polynomial differential operator, and the claim is that the example and the exercise is that p hat annihilates d to the minus d over 2. I mean, you just have to calculate this through, so there's no magic here. It's trivially to check. So IBP identities in the symbolic setup are always trivial to check. Because you just compute this thing, right? So what happens when you hit this operator on this thing? Well, first of all, there are terms when you take derivatives. So there are terms when you take dx1 derivative. So for example, there is a p p squared x1 squared dx1 derivative, right? You also have a minus x1 dx1 derivative. You have this, so this is from here and here. You take a dx1 derivative. What happens when you take a dx1 derivative of this thing? Well, first of all, you get a minus d over 2, and you get a g in the denominator. And then you get the derivative with respect to x1. So what is the derivative with respect to x1? It's just 1 minus p squared x2. Right? Equation for it is up there. And then you have terms when you take the x2 derivative. Well, that's simple. You just have minus x2. Then you have minus d over 2 from the exponent. Then you derive this, 1 over g. And the x2 derivative is just 1 minus p squared x1. And then you have terms where you don't take a derivative. So you have a minus d over 2 from here. Then you have to be careful when you apply this d, you also get a 1 from here, which cancels with this one. So you actually don't get anything from here except for this d1. So you also have minus d1 from there, and then with here with the p squared. And that's it, right? So you get this whole thing acting on g times g minus d to the minus d over 2. Right. So now you can clear denominators. Just multiply with g here instead. So all I'm asking you to do is to check that this polynomial is 0. So that you can do this in 2 minutes. So what is the exercise? This is 0. Okay. So we have found a differential equation for the integrand. And these kind of things, I mean, this is classical non-commutative algebraic geometry. So there's a big theory of how you can find these kind of annihilators of D modules. And I'm not saying it's simple to do in practice. I'm just saying that it's something that's well studied. And this is one way to prove, for example, contiguous relations for hypergeometrics. But what do we conclude? Well, because this is 0, if you have 0 and we integrate 0, we still get 0. So the Mellin transform of p hat g, right? Because this is 0. Of course, the integral of it will be 0. But the point is that I've written p in a form where you can use this integration by parts rules to rewrite these terms, right? Because how can I rewrite this? Well, let's just look at this first part here. Well, this thing here is just a multiple, and this x1 d by dx1 operator, which just comes multiplying with n1 after the Mellin transform. Right? So this is just minus p squared. And then you have 1 plus n1. So n1 is what you get after Mellin transforming this one. Minus d over 2. And then you still have an x1 in the Mellin transform. But you know, this just means that you multiply with n1 and you shift by 1. Okay. And then you have this other term, which is simply n1 plus n2 minus d over 2 with no shifts. Okay. But now recall that this, so this gives you an equation which tells you how you can rewrite m with n1 shifted in terms of the original one by simply multiplying with a little rational function. Right, so you conclude that if you shift by 1, well, let me not write the argument. And this for this argument g to the minus d over 2, you get n1 plus n2 minus d over 2 over minus p squared, 1 plus m minus d over 2 n1. So in other words, it tells you that you can reduce the Feynman integrals of the bubble with shifted arguments to the one without shifted arguments. Right? So remember that in order to get from this Mellin transform to the original Feynman integral, all you have to account for is this little gamma prefactor. And this d over 2 doesn't play any role anyway, because d is always the same. Only from the denominator you get some extra factors when you shift the n's to translate between m and I. So the exercise that you can do is to check that the equation you get from this for the integral, I mean, I can write this down. So the actual integral, the Feynman integral with n1 plus n1 plus 1 and 2. So it's the same factor times an extra 1 over d minus n1 minus n2 minus 1. So the formulas for integration by parts always look a bit more complicated when you write them down for the Feynman integrals as compared to just these Mellin transforms. So you get this extra factor times I of n1 and 2. And you can, as an exercise, check that this is the same thing that you get the same relation from your momentum space way of doing things. Yeah. Of course, you can also take the gamma functions that express this integral and check that this is the correct equation. Yeah, so what I want to bring across here is that you can do integration by parts in this parametric representation, and you get the same structure. So you get difference equations which relate the integrals with integer shifts of the arguments, and the coefficients of these relations are always little polynomials in the n's and the dimension. So it's exactly the kind of structure that you get also from IBP momentum space. And you can prove that all of these, that the momentum space way of doing it is a special case of this. So whenever you have a momentum space IBP, you can literally explicitly write down with some symbols and some definitions of what the corresponding operator P is. So this is one way to prove that this naive symbolic momentum space way of doing IBP is actually valid and gives consistent results with this. Any questions on integration by parts? Maybe. Yes.
The fact that this differential column in the X space is connected with another, this differential operator is connected with a differential operator on the P's. Create kinds of a map between the X space and the P space?
Sure. I mean, this is the Mellin transform. It's called the Mellin transform. So you do the Mellin transform either on the functions. You integrate a function, you get a function of n's. So the polynomial, the u and f's become, which are functions of the Schwinger parameters, now become functions of the dimension and the propagator exponents, the n's. And in the same way, you also get a map on the level of operators, which map you difference operators to differential operators or vice versa. And that's just called, again, I call it the Mellin transform. I think D-module people call it the algebraic Mellin transform. But because the point is, if you write down the algebra of differential operators, it's just the Weil algebra. If you write down the algebra of the difference operators, naively it first looks a little bit different, but if you just identify, according to these rules, the generators, you actually see they are isomorphic as abstract algebras. I think thematically, and let me just postpone the break for 2 more minutes, because then we do something completely different. So just to summarize in a couple of remarks, as you know, integration by parts is a very important step in calculations of scattering amplitudes, and it's actually right now it's a very exciting time. There's a lot of developments in integration by parts, but seriously, you have to have another lecture on this. It's really, it's impossible to deal this with any kind of scope in the short amount of time, I'm afraid. But let me just say some general things. So the crucial, for any of this to make sense, so we needed analytic regularization. Right, for all of this to make sense. If you don't regularize, if you choose integer values for the dimension or for the indices, you will be sitting on divergences and expressions will not make sense. So by doing this analytic regularization, what we have gained is that now we have well-defined meromorphic functions, and we can talk about identities of meromorphic functions, no matter how many poles they have. And then, of course, in the end, if you specialize, I mean, of course, it may happen that you want to evaluate the function exactly at this pole, and then you have to Laurent expand. But the point is you don't have to worry about this, right? In this whole integration by parts business, you never have to worry about, if you do it symbolically, you never have to worry about, is this thing actually convergent at this point or not? You just treat these equations symbolically, and the point is I just explain why this is justified. So we need analytic regularization. And once we do this, the vector space, we can think of a vector space now, which we get from the Feynman integral where we shift the arguments right. So what I mean here is that you take your Feynman integral of the n's. The n's are my complex parameters. I think of variables in the complex n space. And now you shift by an integer in any of these slots, right? So we had this original Feynman integral, then we had another Feynman integral, which we got by an integer shift. And we found actually these are not independent, they are related by a rational function. So when you look at all of the shifts of all of the Feynman integrals, so you start with the Feynman integral, you do all integer shifts, then this linear space over the field of rational functions. So when you look at rational functions in the n's and the dimension as your coefficient ring, then this vector space is a finite dimensional vector space. So this is a big theorem. And again, this is first proved in the literature on algebraic D modules. So, I mean, you can make different claims. You can trace it back to Bernstein, but I think in the most explicit way, in this difference equation type of way, it was done by Louiser and Sabat in 91. And actually, you can even give a nice formula for the dimension. So the dimension is easy to compute. So you can actually look at the polynomial and define some Euler characteristic, which you can compute in many different ways, which gives you this dimension. Unfortunately, this is not what makes people happy, because what people always do is that you try to stratify your problem by subtopology. So the idea is you want to treat as many of these n's as integers as possible. And as soon as you start putting them on integers, you have these funny relations that if you have an n which is actually 0, it means that you contract the edge and you have a subgraph or a subtopology, as people like to call it. And then you separate. You have your nice vector space, and now you chop it up into many little subspaces which hold these integrals which come from these subtopologies. And that makes the counting much more complicated. But in any way, this is not the bottleneck. The bottleneck is to compute the reductions, to really get the equations which solve you your input integrals in terms of some basis of this vector space. And there are many different strategies, and as I said, unfortunately, if you have specific questions about those, I mean, I invite you to approach me and we can talk about that. But for the purpose of this section in my lecture here, I just want to say there's many different methods. There's extremely powerful programs. There's a huge variety, actually. This is very nice. So there's many different programs that do integration by parts in many different ways. There is, well, I don't even start listing them because there's way too many and I will forget some. What you should always separate, though, is there's two different questions. One question is how do you get the reductions? The second question is what are your basis integrals that you want to solve for? Right? Because you have a vector space with the basis, you can pick any basis and you can express your amplitude in whatever basis. So the question that's raised occasionally is, well, what is the basis that you should be aiming for? So let me just make one comment on that before we finish the section. And then we have a break after 1 hour, not after 45 minutes, but that doesn't matter. So I think I've seen 3 different suggestions in the literature of how to choose bases. No, 4. Huh. So there's one suggestion which just comes out of the Laporta algorithm that you make So the way this algorithm works is that you have to make put some order on these integer shifts so that you prefer certain integrals over certain others, and you try to solve your system with respect to that order. And then the algorithm will naturally output you something that has minimal basis with respect to that order. But of course, this is a choice of basis that is motivated by a method. So it may not be physically the most meaningful. So other suggestions for choosing bases, I think the one that is most commonly used and is most effective when you use differential equations to compute Feynman integrals, especially when you have a iterated integral representation in mind, is what's called the uniform weight or uniform transcendentality bases. Bases, choices. So one way is the idea that you want to choose your master integrals uniform transcendental weights So here the idea is that you want to choose the basis such that the differential equation for the master integrals becomes very simple. So with this one you optimize the differential equation. So in order to talk about, or maybe it's also called, this is sometimes called the canonical form of a differential equation. Unfortunately, Nima Akani Ahmed is using this for a very, very different thing. So I don't want to use this term too much, but so here the goal is to optimize the differential equation. And whenever you can achieve this, it's extremely useful. So you have complete control over the differential equation. Another thing that I can't help mentioning is finite phases. For some reason that has not been used systematically for very long. But we have discussed that there is always a region where the Feynman integrals converge, so you can also choose your basis in terms of finite integrals. And one advantage of this is, for example, is numeric evaluation. Because you don't have to worry about resolving any poles in epsilon. Right? You have a convergent integral, you can throw your Monte Carlo right at it. And if you use sector decomposition programs which are around on the market, it happens that it seems to be the case that they're actually much more efficient and give you more accuracy when you choose a finite basis to express your answer. Also, a finite basis shows you structure. So if you expand your scattering amplitude in a finite basis, you can read off the order of the epsilon poles from the coefficients in this basis. And what you find is that the higher order poles tend to come from the simpler Feynman integrals. So the poles of the poles come from simple integrals. I mean, this is more like a kind of vague statement, but we have seen this very recently in the calculation of the cusp anomalous dimension in QCD. So this is some very important property to characterize infrared divergences. And for example, if you do this in a traditional approach, you have to compute several hundred master integrals. But if you choose a finite basis, it turns out that actually for the 1 over epsilon squared poles that give the cusp anomalous dimension, the most complicated integrals do not even contribute. So you actually simplify your life a lot. And you eliminate certain integrals from the calculation in this approach. And the third application, which is important for tomorrow, is integration. So if you want to compute a Feynman integral by taking these parametric representations, which we have studied for 2.5 days, and you want to actually compute the integral from this representation, well, you better have the integral well defined. And as I explained to you, you can use integration by parts to always find an integral representation which is convergent, and you get the well-defined integral, and then you can start doing algebraic geometry. So a finite basis that also has the advantage that you can think of the integral, just take this integral representation not just as a technical tool to derive IBPs, but really to compute the integral. So for that, you want to have gotten rid of all kinds of divergences. So that's the end of the advertisement and the beginning of the break.